Hi everyone, welcome to week 8's lecture. This week we learned the two-sample t-test. It's similar to the one-sample t-test that we saw last week, but this is just another tool to add to our bag. So again, this will be the third hypothesis test. We saw the one-sample z-test, the one-sample t-test, and now the two-sample t-test. Quick outline for today. I'm going to review the material in the book. The readings for this week, it's Gersman's chapter 12, comparing independent means. We'll do some examples from the book, and then we'll review the assignments that are due. Before we get into that, there's the 10-step hypothesis test procedure that we've seen the last couple of weeks. So it's going to apply again this week for the two-sample t-test. So again, if you haven't printed this out or kept it somewhere else or made a note of this, please do so. I'll be following it when I do the examples today. And this week I'm going to introduce another 5-step procedure, or another procedure with 5 steps. It's a general statistical procedure. And this is a little bit more than the hypothesis test procedures, the 10 steps. There's a little bit more thinking that you have to do. We've already kind of been doing this, but I just want to officially formalize it as the general statistical procedure that you should follow for answering any of the questions in the quizzes or the homeworks or the project, or even just once you enter leave the class and interact with any data. The first thing that you always want to do is do some exploratory data analysis. Create some box plots, some density charts, calculate the mean, the standard deviation, other summary statistics, the median, histograms, things like that. Then we're going to formulate our statistical hypothesis that we want to test. This is basically, after looking at the data, you're going to decide on a null hypothesis, and maybe you'll decide at the same time the alternate hypothesis for some statistical test that you want to do. Now, we haven't talked about correlation yet, but for example, if I have two quantitative variables and I calculate the correlation coefficient as part of my exploratory data analysis and it comes back as 0.4, which is a moderate correlation, then the statistical hypothesis that I might formalize is that, that there is a non-zero correlation present in this data set. That's actually the alternate hypothesis. The null hypothesis for that test is that the correlation is 0, and the alternate is that it's not 0. But you're formulating a statistical hypothesis. You're starting to think about the data in a way that you can utilize a test to help answer a question. That's what formulate statistical hypothesis means. Step 3 is identify the appropriate statistical test. In this example that I just mentioned, it's the t-test for the correlation coefficient. And again, we haven't reviewed that yet. But a test that we have reviewed is the one-sample t-test. So maybe I have some data. It's on GRE scores on the quantitative section. And I'm asking, you know what, 600 is a good score. Does this class or the students that I have the scores from, is their average score greater than 600? That's a perfect example of something that I can use the one-sample t-test for. My null hypothesis can be that the mean score is 600. My alternate hypothesis is that is not 600. And the correct test for that is the one-sample t-test. Then we want to verify the test assumptions. Now, this is kind of part of the 10-step hypothesis test procedure, but verifying the test assumptions we should do even before we start to conduct the hypothesis test. As soon as we identify a statistical test that maybe we might want to do, we should immediately take a look at the test assumptions. So I'm going to be following these 5 steps today. Again, you already kind of have been following this procedure, but now I've just formalized it a little bit. So finally, let's introduce the two-sample t-test. This is used when you don't know the difference in the true population means between two different populations, but you have some data from each of the populations and want to test to see if the data disproves the hypothesized mean difference. Okay, that's a lot of stuff. What does that actually mean? Basically, you have two different populations. A good example of this is maybe we're talking about salaries and we're talking about gender distributions of salary within each gender. Sorry, my verbiage is not so good today. We're talking about a discrepancy. That's the word I was looking for, in the salaries between males or men and women. So we have two different populations. We have men is one population, and we have women is the other population. We don't actually know the true mean salary for men or for women doing a specific job. Let's say we're talking about cardiac nurses. Uh, so we're going to collect some data, and we want to see whether or not there's a difference in the average salary for the men and the average salary for the women. Ideally, the difference should be zero. They should be the same, right? So the two sample t-test is what we can use to test this. The assumption is very similar to the one sample t-test, or that the data, the samples must be simple random samples, or could be weighted, but for our purposes, they must be from a simple random sample. Again, it's not really an assumption, but typically we do the t-test when the standard deviations are unknown. When you know the standard deviations, we can use the normal distribution. We talked about that last week. And again, with a t-test, the sampling distributions for each sample needs to be approximately normal. Now, the actual assumption is just that the distribution for the difference is normal. But it's actually will follow that if each of the separate populations follow a normal distribution, then their difference will also follow a normal distribution. So that's the much easier thing to verify. We have two different populations. We have data from two different populations. We basically have two different samples, right? And we know how to verify whether or not data from a sample is normal or not. We know how to calculate the density curve and the QQ plot, specifically the QQ plot, and we know how to evaluate that to assess normality. So we'll be doing that for both samples when we conduct a two-sample t-test. And both of the samples need to be normal. So again, an example, I talked about the salary. Another one would be we're conducting a study. We have two different groups, an experimental group and a control group, and we want to know if there's a difference in the mean weight loss between the two groups. Or, for example, have GRE scores, and do math majors from public schools have equal differences in verbal and quantitative sections when compared to math majors from private schools. Now, this is a little bit more complicated. This is actually almost a combination of the two-sample t-test and the paired t-test that we saw earlier. Let's just talk about math majors from public schools. They have the GRE verbal section scores and the GRE quantitative scores because it's the same students taking the test with a verbal and a quantitative score. That kind of sounds like something that we would do a paired t-test for, right? The one sample paired t-test. So if we do that and we have those differences, now we do the same thing for math majors from private schools, and we have differences from the private school math majors, and now we have two samples again. We have differences for public school math majors and differences for private school math majors. So now on those differences, we can do a two-sample t-test. So I hope I didn't lose you there, but again, this is an idea of the two-sample test. You have to have two separate samples. But the fact that we could combine them with the idea of paired sample is kind of like how we would combine different probability rules earlier in the class. You can take these simple ideas and construct some more complicated things with it that are really quite powerful. So just some notation. None of this should really be new to you. The only thing I want to point out is the sample variances. Because we have different groups, we are using the subscript of 1 for group 1 and 2 for group 2. Those subscripts might change, but the idea is that you have two separate groups. The sample variance then not only has a subscript, but also has a superscript. So again, the sample variance for group 1 is S sub 1. So S is the standard deviation for the sample in group 1, and that squared. So you see S1 squared. So we'll also see in the book there's a point where it's the sample standard deviation to the 4th power. So it'll be S1 to the 4th. And again, that's with a subscript of 1, the superscript of 2. So again, none of this notation should be too different from anything that you've seen before. The only addition now is that we have these subscripts. And what are the actual components of this test? So statistically speaking, the null hypothesis is that the mean in group 1 minus the mean in group 2 equals 0. So the difference in population means equals to 0. That's a two-sided test that we might do. Or we could even do a one-sided test, which means that the difference in means is greater than 0, their difference is less than 0. So again, mu1 minus mu2 greater than 0, that means the difference in the population means is greater than 0, or less than 0. The alternate hypothesis then, if our null hypothesis was equality, the alternate hypothesis that the difference in means is unequal. If our null hypothesis was that the difference in means is greater than 0, then our alternate hypothesis is the opposite of greater than 0, which is less than or equal to 0. Same thing for if our null hypothesis was the difference in means is less than 0, then the opposite of that is that our difference in means is greater than or equal to 0. Our test statistic is going to be a t value. So how do we calculate that? Well, the difference in the sample mean, so x bar 1 minus x bar 2, remember that's the sample mean from group 1 minus sample mean from group 2, divided by the square root of the variance in group 1 divided by the sample size in group 1 plus the variance in group 2 divided by the sample size in group 2. All of that will follow a t-distribution with a certain number of degrees of freedom with this complicated formula. This is called Welch's degrees of freedom. It's usually, you don't have to do any of this by hand because you've got some statistical software. We don't have that in this class. That's okay. This is a math class, so you should be able to follow this equation. If you have problems breaking this down and plugging in numbers step by step, then please do let me know. But my advice is, again, do step by step. So I would do this in several parts. First, I would figure out what the sample variance from group 1 divided by the group size, the sample size in group 1 is. That's S1 squared divided by N1. That's just this little part right here. I'll do that first. Then I'll calculate this, which is the sample variance in group 2 divided by the sample size of group 2. Then I'll add them together. Then I'll square that. Now I have the numerator. For the denominator, similarly, I'll do the first half first, then the second half, then add them together. Now I have the denominator, then I can take the numerator minus denominator. So there's several steps. Go slow. That's my advice when doing it by hand. And I did it by hand as well in the example problems that you'll see in a little bit. One quick note, for the t, test statistic, this part in the denominator, the square root of the variance divided by the sample sizes, the sum of the variances divided by sample size, that's called the standard error. That's the standard error of the difference in the sample means. That's important. That's going to come up again. That's we're going to see that in the equation for confidence intervals. But again, this idea of standard error is something that we've seen before, right? So if the difference in the sample means is our point estimate, then our point estimate divided by our standard error. This harkens back to talk of the central limit theorem. And again, if you don't want to deal with all of this complicated equation for degrees of freedom, you can use a conservative estimate, which is the smaller of the group sizes, each of them subtracted by 1. So take the group size for the first group, -1, the second sample size, -1. Whichever one is smaller, you can use that as your degrees of freedom. That's going to give you a conservative estimate. What about the formula for power? Well, this is pretty much the same as what we've seen before. Again, this is a t-test, so I like doing something slightly different than the book. We're going to use the t-distribution. So usually this is going to be after the fact. One little note is that if you look in the book, it just uses n. That n is actually the group, the sample size for each group, but sometimes you have different groups, right? So I like using this modification as the total sample size n divided by 2. So basically you're taking the average group size. Delta, again, is the difference worth detecting, and the other symbols you know. The sample size requirement for each group is as follows. Again, delta is the difference worth detecting. We have the sample variances. Now, if your data hasn't been collected yet, then you just have to make guesses on this, which is difficult to do, but not totally impossible. And then we're adding 1 at the end of this. Now, the book asks you to multiply by this factor, degrees of freedom plus 3 divided by degrees of freedom plus 1. That is pretty much always going to correspond to just simply adding 1 to the end of this equation. So that's much easier, so I like that. Also, sometimes we already have the data collected for one group, so we have a fixed sample size in that group, but we're in the process of collecting data for the other group. If you were called in late and somebody said, oh my God, we forgot to figure out what the sample size should be based on our powers and whatnot. Power and confidence and sensitivity and specificity. So you already finished your data collection for group 1 before you calculated this equation. So then group 1 size is fixed. So you can still do the equation, calculate this required sample size, but then you can find out how large group 2 should be by using this equation. And rec is the required sample size that you calculated up here, and N1 is the fixed sample size in whichever group has already a fixed size. Again, if samples haven't been taken or you don't have any information about the sample, you don't know about the sample variances, then you can use your best guess to calculate or estimate the population variances, sigma. Same thing up here for the power. If you don't know the different sample sizes, you don't know the degrees of freedom, then you can just use Z instead of T. For confidence intervals, now again, our test statistic is equal to the difference in sample means divided by the standard error of the sample's means, which means our confidence interval is going to be just that, our point estimate, which is the difference in sample means, plus or minus our T value, which is basically our critical value, times the standard error. And we already have the equation for the other slide, so that's what we'll be using. Let's dive right in and do an example of this. I'm going to do example 12.18. This is on page 291 to 292. We're talking about hemodialysis and anxiety. So apparently, patients who undergo chronic hemodialysis suffer from anxiety, which makes a lot of sense, severe anxiety. So a study was done, this study was done in the 80s, and this is actually from an actual study. You should be able to look this up online. And we have access via GW to PubMed, which is where most of these biological and public health articles are stored. PubMed's a great database, so you can log into, go to library.gwu.edu and sign in, find PubMed, and you should be able to actually find this article. So the study was underdone to see if some set of progressive relaxation exercises had any effect on the anxiety of these patients. So we have some data. They did this treatment to the experimental group, these anxiety relieving exercises, and then administered an anxiety test. Lower scores are better. So we have the experimental group. There were 38 people in the experimental group. Their mean post-test score, or the anxiety score after they've done dialysis and after they have received these anxiety treatments, was 33.42. The sample standard deviation for that group was 10.18. For the control group who did not receive these anxiety relieving techniques, there were 23 people, and their mean anxiety score on this test was 39.71 with a standard deviation of 9.16. And we don't actually have the data, so we can't create box plots or anything, but I still wanted to visualize it somehow, so I just created this plot. It's of the mean, 1 standard deviation above, 2 standard deviations above, 1 standard deviation below, and 2 standard deviations below. So this is kind of like a box plot, but it's just a way to visualize the data side by side. And again, when we look at this, as opposed to just looking at the table, the idea is we're interacting with it in a different way. We're interacting with the data in a different way. And that's the whole point of visualization. So do I think there's a difference? Well, if I just look at the table, yeah, it looks like the control group scored 6 points higher. Low scores are better, so actually the experimental group scored 6 points lower. So it looks like that treatment did have some effect bringing score down. So that's good. When I look at the visualization, though, the data is so spread out that they overlap so much that these are pretty much the same, right? So if there is a difference, it's pretty small is what it looks like to me. So before we forget, we have to do the general procedure. The general procedure, as outlined earlier, is the first step is always to perform some exploratory data analysis. And we just did that. So good job, us. Next is to formulate a statistical hypothesis. So what might that be? Well, we have these 2 different groups, and we know the mean scores for each group. So maybe we think that the mean score in the experimental group is lower than the mean score in the control group. So then the difference is going to be less than 0. So that would be an alternate hypothesis. So a null hypothesis would be the difference in group scores is equal to 0. You could do a one-sided test, but let's just do a two-sided test. Let's say the difference, we don't know if, maybe that anxiety treatment actually doesn't help at all. Maybe it hurts because then people know that they're getting some anxiety treatment. So, oh, the doctor wouldn't be giving this treatment unless I was really anxious. That's going to make me even more anxious, right? So it could be that the effect goes in the other way too. So let's just do a two-sided test. So the null hypothesis is that there was no effect that this treatment had. The alternate hypothesis was that there was some effect, that the difference in means is unequal to 0. In that case, the appropriate statistical test is our two-sample t-test, which is great. That's exactly what we wanted to practice. And then the next step is to verify the test assumptions. So we actually can't verify any of these. We don't know what was done. We have to go back to the paper or maybe talk to the researchers. We don't have the actual data here, but we hope that the people who were selected for each of the groups, that was all done randomly. And we hope that the data look pretty normal. The scores appear normal in each of the groups. So we can't tell right now. So we can only assume this might be something that we need to keep an eye on. So we'll mention that again. Now we can go through and conduct our 10 steps for our hypothesis test procedure. Step 1 is our null hypothesis. That's the mean score in the experimental group. That's mu sub E minus the mean score in our control group. Mu sub C is equal to 0. So our difference in means is equal to 0. The alternate hypothesis that the difference is unequal to 0. What's the underlying distribution? We don't know. It'd be nice if we knew. It'd be nice if they were normal, but we don't know in this case. What's our sampling distribution for the sample statistic? Well, our sample statistic is t, remember. We are going to take the difference in sample means divided by the standard error of the sample means. That's going to follow a t distribution. So our sample statistic is a t. It's got 50.43 degrees of freedom. We can calculate that using Welch's formula. I'm not going to do that here. You can also use the conservative estimate of 22. Now, how to get 22? Well, our group 1 sample size is 38. Our group 2 sample size is 23. The smallest of those is 23, so I do 23 minus 1. And so you can just use degrees of freedom equals to 22. You're going to get slightly different answers than what I have because I used the 50.43, but that's okay. Next, our confidence level for our test. Well, it wasn't really provided, but you know what? I feel like using 95%, that's going to keep my type 1 error rate to 5%. That's pretty good. I don't want to say that this treatment had a difference and then later be proved wrong. If I'm going to write a paper or I'm going to suggest it to my boss, I want to be pretty sure that this thing actually works. And let's calculate test power. So to find minus t, that's inside the parentheses, I use the t inverse function. For the difference worth detecting, we weren't really told what a difference worth detecting is. But the scores, now that I've seen the mean scores, the mean score in the control group is around 40. Maybe you knew that before. And maybe I'm interested in a 10% reduction or a 10% difference. So that'd be a difference of 4. So if anxiety scores come down by 10%, or by 4 points, then I think that these techniques are probably worth exploring, and they actually have an effect. So let's use 4 for difference worth detecting. So I can plug this wonderfully long formula into Excel using the t.dist function to find the cumulative t value. And we already kind of explained this last week, so I'm not going to do it. If you have questions again, you can contact me. What I'm doing here with the t.dist function, and when I'm typing into Excel, it'll match up to everything that's in this formula. So cumulative t, again, that's t.dist with the 1 over here for the cumulative t probability. This is my t inverse plus the difference we're detecting, the square root of the total sample size divided by 2, the square root, all of that divided by the square root of my group standard deviations, or my group sample variances. So this gives me an estimated power or sensitivity of 0.3471. Now the actual power is 0.35, so it's pretty close, right? Remember last week I talked about how this formula is just an approximation. But that's really low. We want much higher sensitivity. How do we get that? Well, the sensitivity will increase to 77% if we increase our difference with detecting to 0.6, and we increase our allowed type 1 error rate to 0.1. So that'll balance our type 1 error rate and our type 2 error rates a little bit better. Remember, type 2 error rate is the complement of the power. So if our power is 77%, our type 2 error rate is 23%. That's still a little bit high, but that's much better than having a type 2 error rate of 65%. So let's go with this. Let's use alpha equals to 0.1. That means our confidence level is 90%. And we're working with the difference we're detecting of 6. So scores on this anxiety test need to come down by 6. That's really what we want the test to identify. Next, we calculate our summary statistic after collecting our sample. So this is the formula for calculating our test statistic, or t-value. It's, again, the difference in sample means divided by the standard error of the sample mean. So basically, I'm just plugging everything into the right spot. And this tells me that my test statistic, or t-value, for this data is minus 2.491. Now, what's the probability that I saw something more extreme? That's the sample probability. Now, this is a two-tail test, so I need something further away from 2.491. So that's going to be the probability that t is less than minus 2.491, or the probability that t is greater than positive 2.491. So for the probability that t is less than minus 2.491, that's just the straight cumulative probability. For the probability that t is greater than 2.491, remember, I can't do greater than, so cumulative probability goes less than, so it's 1 minus the probability that t is less than positive 2.491. That's this part. And this gives me a sample probability equal to 0.0161. Next, our test result. Remember, we always compare p to alpha. P was 0.0161. Alpha was 0.1. Remember, we adjusted it up. And p is less than alpha. Therefore, we're going to reject the null hypothesis. So in summary, we have a test that was designed to detect a difference in post-test scores of anxiety of 6 or higher with 90% specificity and 77% sensitivity. In this test, we find a statistically significant difference in the mean post-test scores between the experimental group and the control group. However, due to lack of the original data, we were unable to verify the assumptions of the test conducted and therefore interpret the results with some caution. But it appears that the experimental group did have lower scores, and a 90% two-sided confidence interval for the mean difference in post-test scores in experimental group minus the control group is minus 10.52 to minus 2.06. That means a 90% confidence interval implies that the experimental group will score anywhere between 10.5 points lower to 2 points lower than the control group. Again, that's a 90% confidence interval for the actual difference. So let's do another example. This time, let's do example 12.24. This is on page 293 to 294. I know the slide is really busy. I'm going to talk you through it step by step. This was a study done on daily activity levels. And we have two different groups. We have a lean group and an obese group, and we have measured how much time per day they stand or walk. We want to see if there's a difference. If lean people stand or walk more than obese people. So we have our data here. This is just our data table. The first thing, do some exploratory data analysis. So we have two groups. We have a quantitative variable, so I'm going to do side-by-side box plots. So this is side-by-side box plots in Excel, and just looking at them, it does look like the lean group does walk a lot more, right? The entire box is above that for the obese group. Then I did the same thing in Google Spreadsheets using the statistics package. Now, if you don't know how to use that statistics package, that add-on, I have another video that I created for that. So definitely take a look. I posted that in week 7. The box plots look a little bit different, don't they? The obese group looks pretty similar, but the lean group, the box stops a little bit sooner than the version in Excel. Not only that, the line doesn't go down anywhere near as far, and I have these two dots. Why is there a difference? Well, it's because these two dots are outliers in the lean group. So the default setting in the statistics package is to have the line going to what's called the interquartile range, the IQR, which is 1.5. times the difference between the third quartile and the first quartile, and to draw a line to whatever observations are within that range. Any observations outside of that are outliers, and you just put a little dot there. In Excel, we don't do this. We just get the minimum, the first quartile, the median, and this X is actually the mean, the third quartile, and the maximum. So the lines go all the way to the maximum minimum versus, again, Google Sheets, which the lines stop at the interquartile range. You still get the same idea from both. If anything, I think the Google Images, sorry, not the Google Image, the Google Spreadsheet box plots might lead you to say, yeah, the lean group, the whole box is above that of the obese group. And aside from these two outliers, literally everybody in the lean group walks or stands more than everybody in the obese group. So that's pretty strong. Same thing in the Google spreadsheets with the statistics package. We can calculate or create histograms and density plots and QQ plots. So up here at first we have the lean group, the density plot, which does not look normal at all, but when we look at the QQ plot, the normal quantile plot, there's really just these two outliers that are messing it up. Everything else is on a pretty straight line. So that looks, pretty close to normal. Again, the sample size is really small, so that's kind of concerning, but aside from these two outliers, it actually looks pretty normal. Next, the obese group, which looks a little bit left skew as well. And looking at the QQ plot, again, it looks relatively normal except for these two outliers. So both of these, I don't think these are massive departures from normality. Remember the robustness of this normality assumption. But we do seem to have a couple outliers in both of them. But what's really more concerning is the small group size. Remember, we wanted group sizes somewhere around at least 10, even if the data was normal, or closer to 30 if the data skewed. So, with these couple of outliers, maybe the data skew a little bit. Maybe they're both a little bit left skew. So sample sizes bigger than 10 would have been nice, but I don't think it's a huge deal. Next, we have some summary statistics that the statistics package or add-on calculates for us. So it tells us that the mean standing or walking minutes per day in the lean group is 525 compared to the mean of 373. The obese group, these are the sample standard deviations, and it actually calculates the standard error for the mean for each group for us too. So that's kind of nice. And again, the standard error for the mean is the standard deviation divided by the square root of the sample size. So you can calculate that yourself just to make sure it's been done correctly. So after looking at all of this exploratory data analysis, it appears to me that that both the lean group and the obese group, the number of minutes spent standing or walking, they both seem to come from normal distributions, which is good. And it certainly does appear that the average time spent standing or walking in the mean group is greater than that, in the lean group is greater than that in the obese group. So again, remember your general procedure. We just did the exploratory data analysis. It was pretty thorough. Next, it's formulate a statistical hypothesis. And we have that. We just talked about how we think that there actually is a difference in the mean standing or walking time. We think that actually the lean group standard walks more. And I apologize here for the subscripts not being correct. But our null hypothesis will be that the difference is equal to 0, and the alternate hypothesis that the lean group walks more, so the difference is greater than 0. The appropriate statistical test is the two-sample t-test, and we already verified its assumptions. Remember, the main one is that both of the data sets should come from a normal distribution. The QQ plots look okay, but the sample sizes are small, so use the test with caution. We'll make a note of that in our summary and conclusion as well. Now we can move on to the 10-step hypothesis test method. First, what's our null hypothesis? That the difference in the mean time spent sitting or walking in the lean group minus that from the obese group is equal to 0. The alternate hypothesis is that the difference is greater than 0, that the lean group actually stands or walks more. The underlying distributions, they're both approximately normal. This is great for our central limit theorem, which implies that our sampling distribution for the sample statistics, again, this is going to be a t distribution. Using Welch's formula, we find that there are 15 degrees of freedom, or using a conservative estimate is 9. Now again, how to get 9? Well, both of the group sizes are equal, so I take 10, which is the group size, minus 1 of 9. The confidence level, so it wasn't provided to us, but let's use 90% confidence this time. I'm willing to take on a 10% chance that I'm wrong here, but anything that I can find that may help obese patients lose weight or be healthier, definitely want to advocate. Now, I don't want to just advocate anything and everything, so let's use 90% confidence. Knowing that, let's calculate test power. First, we need to find a difference worth detecting. I think that if there's a difference of 60 minutes, so if the lean group stands or walks 60 minutes more per day, that's 1 hour per day, then I definitely want to find that out. Then I can tell my obese patients, you need to make sure that you are standing or walking an extra hour every day. Just go on an hour walk. Call up one of your friends or family members, talk to them for an hour, but walk while you talk, or put on a nice 60-minute playlist and go walking, and that's really going to help. So if I have that, my 60 is my difference worth detecting, and my type 1 error rate of 10%. It turns out the test power is just about 56 or 57%. That's pretty low. So how can I increase that? Well, the test power will go up to about 82% if I increase my difference worth detecting to an hour and a half or 90 minutes. So let's run with that. So I'm trying to conduct a test to see if there is a difference in the lean group, if the lean people walk 90 minutes more per day on average than the obese group. Next, let's collect our sample and calculate our summary statistic, our t-value. So again, I'm plugging everything into the right spot, and this tells me that my test statistic here, my t-value for this test is 3.808. What's the sample probability? Well, this is a one-tail alternate. I'm interested in whether or not the lean group walked even more than the obese group. So I'm interested in a t-value even greater than what I saw. That's more extreme. So the probability that I get a t-value greater than 3.808, I can't just calculate that. Remember, cumulative probability only works less than. So probability that t is greater than 3.808 is the same as 1 minus the probability that t is less than 3.808. So this is what I'm typing into Excel. And this will tell me that the p-value for this test is 0.000858. That's really small, and certainly much less than our type 1 error rate, which was 0.1. Since p is less than alpha, I'm going to reject my null hypothesis. So in a test designed to detect a difference in mean standing or walking time of 90 minutes or higher with 90% specificity and 82% sensitivity, we find a statistically significant difference in the mean standing or walking time between the lean group and the obese group. However, due to small group sizes, we must interpret the results with some caution, but a 90% one-sided confidence interval for the mean difference in standing or walking time for the lean group above that of the obese group is 98.8 minutes or greater. So it appears with 90% confidence, there's 90% likely that lean people stand or walk at least 98.8 minutes more than the obese people. So after doing those two examples, let's talk about what you need to do on your own for this week. We actually just have a quiz this week. It's not even on the 2-sample t-test. It's on the previous 4 chapters, chapters 8, 9, 10, and 11. So again, this was hypothesis tests and sampling distributions and the central limit theorem and confidence intervals, and then the 1-sample z-test and the 1-sample t-test, as well as the paired t-test. So that's everything from chapters 8 to 11. You're going to have a quiz on that. You can find more information about the quiz in the weekly sessions. Remember to take the quiz before midnight on Sunday night. You have this week. So the quiz is going to close Sunday at midnight, at the end of the day on Sunday, technically 11:59 p.m. Eastern time on Sunday. In the meantime, we have a discussion board. So you can ask any and all questions concerning any of the material that you've read or learned about or heard me talk about in chapters 8 through 11. Definitely use that discussion board to interact with your fellow students, ask questions of me. I'll try to post some other helpful hints in that discussion board as well. Just coming up next week, we have problem set 4, which is going to cover chapters 12 and 13. So that's going to cover this 2-sample t-test, as well as what we're going to be talking about next week in chapter 13, which is ANOVA. It's basically an extension of the 2-sample t-test into many sample, a difference in means across multiple groups. But don't worry about that for now. And a week after that, in week 10, is project preliminary results. So by week 10, we'll have several tests under our belt: the 1-sample Z test, the 1-sample T test, the 2-sample T test that we just did this week. We're going to have ANOVA, which is what we're talking about next week, which is identifying a difference in means across multiple groups. And then I believe we're going to have correlation under our belt as well. So there's a couple of questions in the project, a couple hypotheses that can be answered using these tests. So you're going to take a stab at doing those statistical tests and summarizing them and presenting the results. And then I'll give you some feedback on how to do the test. And then you can go back, and in the last couple of weeks in the class, you can finish up the rest of the test and then put together your final project. So again, this week we have a quiz that's on the material that we saw in the last couple of weeks. Next week we have a problem set covering the material we saw this week. So again, just to review what we talked about today, we talked about Gerstmann's chapter 12, comparing independent means. Now, there is one thing in the book that I didn't talk about, which is an equal variance procedure, or pooled variance. Now, some of you might have seen this before in your previous statistic classes. If you took 2117, we talk about pooled variance too. The reason I didn't mention it is there's really no reason to ever use it. It's computationally a little bit easier, but we use computers and calculators these days. And usually we're using statistical software, so it really doesn't matter. The computational complexity is just completely taken right out. So there's really no reason to ever use the pooled variance. It's actually much harder, because if you do want to use pooled variance, then you have to do a different hypothesis test, because using pooled variance has an assumption that the population variances are equal to each other. So then you have to do what's called an F test for equal variances, or another one of the very many tests that exist for equality of variances. And you need to do that before you can even do the 2-sample t-test. So it's better just to do the version that I presented. It's called the unequal variance 2-sample t-test, if you're being particularly pedantic. So we talked about everything except that kind of unnecessary pooled procedure. We talked about this general 5-step process to statistical analysis, and we reviewed our 10-step hypothesis test procedure. We did a couple examples, and then again, we reviewed what homeworks you have to do this week. It's just the quiz and the discussion board. That's all for this week. Next week, we'll come back. So we saw the 1-sample t-test, the 2-sample t-test for difference in means. Next week, we're going to talk about what happens when we have more than 2 samples. Let's say we have 5 different samples, 5 different populations, and we want to test the difference in means. We'll talk about how to do that next week.